So for number 1, it says, using the letters in the word square, how many 6-letter arrangements with no repetitions are possible if vowels and consonants alternate beginning with a vowel? So there's 6 positions to fill, so you could think of it like the slot position with 6 positions. And the first position you're going to fill with a vowel. How many vowels are there?
3.
In the word square. 3. Very good. And if it's alternating, then you have 3 options in the second position for the 3 consonants. And then it goes down by 2, 2, 1, 1, and you multiply that to get 36 different ways. Okay, so how'd y'all do on that?
I got 360. So, I don't know.
Yeah, that's 30.
Maybe just multiply wrong, something like that. Okay.
Yeah, it's 36.
Okay, so number 2. So we have Amy, Ann, and Dora, so 3 girls, and then we have Al, Aaron, Bob, and Roy, so 4 boys. Okay, so determine the number of ways the children can be arranged in a line with the following conditions. So the first one is if a girl is always at the head of the line. So again, the number of ways, and we have 7 positions to fill. Okay, so how many ways can a girl be at the head of the line? 3, because there's 3 girls. Very good. Then beyond that, there are no requirements. So the second position is going to be the leftover 6 people, right? And there's 6 choices there. So 6, 5, 4, 3, 2, and 1. And that's going to give you what?
2,260.
210.
Okay, y'all are all getting something different.
2,106.
2,160? That sounds about right. Okay. Did y'all get that? No?
Yeah.
Did y'all follow this process with the multiplying?
Yeah, that's
this one?
what you get.
Okay. Okay, good. Now, does that make sense?
Yes.
So you have to think about your requirements. Here, you had to have a girl in the first position, but then beyond that, there were no choices, or there were no requirements, I should say. Now, what about Roy is always at the head of the line? So again, 1 option, Roy. Roy's your guy. He's your line leader, right? Okay, and then beyond that, the 6 other people can be arranged however, and there's all those different combinations of arranging those 6 people. It's just 6 factorial.
712.
Okay, so 700, is that what you got?
Yes.
That sounds about right. Okay, so how are y'all on that? Could I have done 6 times 5 times 4? Absolutely, but that's the same thing. Okay? Now, 4. 4 is probably the hardest one. What is the probability that a child whose name begins with A is at the head and the rear? This should say rear, guys. And we're looking for probabilities here, not combinations or counts. So we need to think of it as the probability for any event is the number of ways that the event can occur out of the total combinations. So we need the probability for finding an A at the beginning and an A at the end of the line. Okay? So how many ways can you arrange those 7 people where an A is at the beginning and an A is at the end of the line? How do we do that?
4 over 7 times 3 over 7?
4 over 7 times 3 over 7? Okay. Okay, you are on the right track, and we'll come back to that thought in just a second. That's using probabilities. Here we're using counts and combinations. So let's do it this way, and then we'll come back to your thought process. So this is for the numerator, guys. How many ways can I get an A here and then also an A there?
4 times.
So 4 here, and that means only how many are left here? 3. Okay? Then the middle part doesn't matter, right? It can be anything. And I have 5 people left over, so 5, 4, 3, 2, 1. That's the numerator. So what does that give you? What?
1,440.
1,440, very good. And then the denominator is going to be the total combinations, and that's just really what? 7 factorial. because you have 7 times 6 times 5, okay? So I don't really have to do all of that. It's just going to be 7 factorial. And when you do the math there, what do you get?
5. Oh. Like the decimal?
Yeah, the decimal's fine.
0.29.
Okay, 0.29, that's rounded, so it's an approximation, so if you use a little approximate symbol. So that is one way to do it. The other way to do it, I'll kind of scroll down and give y'all some. So this is another option for number 4. What is the probability to place a female in the first position? 4 out of 7. So this would be filling the first spot. Then what about the 7th spot?
3 out of 7.
I'm using a female here as well, but I've already used one there, so don't I only have 3 out of 6 left? Okay. Then for the others, I have, no, really it doesn't matter where I put anybody here, right? So I have 5 people left, and I have 5 position, and I have 5 people and 5 spots. So that's going to be 5 out of 5, because it's going down. Then 4 out of 4 is kind of weird, isn't it? 3 out of 3, 2 out of 2, 1 out of 1. So all of these just basically multiply to give you a 1. And then when you do this, you get 12 multiplying 4 times 3 and then 7 times 6. And this is the same, approximately 0.29.
Yep.
Same answer, just a different approach. This is sort of new-ish. Okay, some of y'all kind of remember it, but we're going to be learning that today. So this is the situation when I multiply 4 over 7 times 3 over 6. Why am I changing both the numerator and denominator here?
Because you already used one person.
I already used one person, and that person was a female. So those two events, these two things are dependent on each other, right? So whatever happened here is going to impact what happens in our last spot there. Okay? Now finally, let's do number 5 here. What'd you get for that one? There's only one way to guess it right, and how many ways can you arrange it? You're choosing 5 from 10. You're choosing 5 from 10. And order would matter, okay? So it's just a permutation. So how'd y'all do on that? Okay? All right. So let's do this. I want to get to the lesson first because every class period today we've run out of time for the lesson. I'd rather you be able to keep moving, hold on to your questions, and we'll come back and answer those questions. But some of this is going to start to gel for you anyway as we go throughout it, okay? So what I'm going to do is I have a note sheet that we're going to kind of work together, or some notes we're going to take. So take out a sheet of paper.
Can we take notes on here too?
You actually can take notes on there. I don't really know what the best way to do it would be, because you just want to bring up a blank sheet basically, right? Like that's what I do here. I pull up a blank PDF of a piece of paper so I can write on it. So there may be other ways to do it where you can just bring up a blank screen. And absolutely that's fine. Okay, now, so y'all kind of stay with me. I'm going pretty quickly. We have a bag of marbles. And in that bag of marbles, we have 4 red, 2 green, and 5 purple. I want to know the probability to get a red on the first draw or selection and a red on the second selection. So I'm drawing 2 marbles essentially. 1 marble. Now, here's the question. Am I putting the first marble back? It matters a lot, doesn't it, how you approach this. So I'm going to replace the marble. No, I'm sorry, I'm not going to replace. So sorry. So without replacement. In a minute I'll talk about what it would look like if I did replace it. So without replacing the marble, tell me the probability there. So take just a second and figure that out. how many of you said, well, there's 4 reds, so 4 over 11, because there's 11 total. And then what'd you multiply for the second one? 3 out of 10. Very good. So the probability for red on the first selection is pretty straightforward. It's the second one. Because we just got a red, what's happening with the second probability? It changes, doesn't it? These are not independent events. So anytime you take out something and don't put it back, the next event and its probability are going to be impacted by what just happened. That is not independent. Okay, so independence does not exist here. Okay, now, if I had replaced, let me kind of just put this off to the side in a slightly different color. So versus replacing. If I had replaced, what would it look like? 4 out of 11 times what? 4 out of 11. Very good. So it's kind of important to know the distinction. Okay, here, these are independent events. And then over on the other one, these are going to be not independent. Not independent events. So basically what happens on one trial or one selection is going to impact what happens the next time. Okay, so without replacement, these are not independent.
Would you just like multiply it and then divide and like put it as decimal?
Yeah, you could just multiply across, so you get 12 over 110, and then you could either simplify the fraction or just put it in your calculator and get a decimal form. Okay, probabilities can be given in either fraction form or decimal form. They're both the same. It's both just probabilities. Okay, now, so let's go back, and I'm going to show you the formula we kind of just learned. You may not realize it, though. So this is a new formula. It is a new formula, but you've been using the process. So y'all have done stuff like this before. It follows a formula you just didn't know you were using, or maybe you did. Not really quite sure about that. So for 2 events that are not independent, you are going to take and say the probability of A and B occurring is going to be equal to the probability of A times the probability of B given that A just occurred. So this is a new symbol. It means given. It may not be new either, because I know y'all done this before with two-way tables in the past. So 2 events that are not independent, the probability for A and B to occur is equal to the probability of A times the probability of B given that A just happened. So the probability to get a red, given that you just got a red. So that's the formula. Okay, so 2 events that are that are independent, what would I do to modify this formula?
Oh, you wouldn't say that the A has already been given you.
Very good. Awesome. Very good. Okay, so I'm going to highlight this. This little piece right there, I hope that's not too dark, is what's going to go away. So the probability of A and B is just probability of A times probability of B. I don't need to know that A has happened because it doesn't change the probability of B if A has happened or if it hasn't happened. It doesn't really matter. There's no dependency there. So the way that you would modify that formula would be this. 2 events that are independent would look like this. Would be the probability of A and B occurring is equal to the probability of A times the probability of B. Now, you guys remember when you do the probability of A and B, you multiply. What about the probability of A or B? You add. Okay? That's not today's lesson, but I just wanted to start to kind of help you categorize things in your brains. Okay, now, so if you replace a marble, when you make your second selection, it's like you're starting fresh, right? There's no dependency on what just happened. When you don't replace the marble, then you have dependency, or you have two events that are not independent. So that's pretty straightforward to most students. I'm going to give you in just a second a table. Let me just show you what this looks like. Just so you'll know, what if we have a situation like this, where we're trying to see if there is some sort of relationship between being right-handed, left-handed, and playing a musical instrument? Is it the case that more left-handed people are musical? Maybe they're more artistic, something to that effect. You're basically studying and examining relationships, and you're looking for independence or the lack thereof, okay? Do you see this one's not as straightforward? You have to use the little formula for this, okay? We're going to test for independence. So I'm going to show you how we're going to test for independence in a case like this. Okay, so back to this. There are two tests for independence, and I'm going to use them both for you today. Okay, so two tests for independence. And I will tell you, this is one of the things that students sort of struggle with in this unit. They can never remember these tests, okay? Today, I want you to focus on just using the tests. Don't worry about memorizing them. You can memorize them later. Okay, so the first test is my favorite. They don't have names, so that kind of makes them hard. We'll just call this test 1. Does the probability of A equal, so it's a question mark, the probability of A if B has already happened? So if B happening doesn't change the probability of A, do you see how they could be equal, and that would mean they are independent? So I'll say that again because that's important. If knowing B has occurred does not change the probability for A to occur, then we know that they are independent events. Okay? Now, let me give you another example that I think is going to make even a little bit more sense. We're going to do this in just a second as well. So when you have bugs on your plants, you know, farmers spray with insecticides, right? So you would think that the probability for aphids are little bugs. So you would think that the probability for a plant to be infected with aphids would go down if they have been sprayed with the insecticide. So in a minute we're going to test and see if you get a different probability for being infected by bugs if the spraying has occurred versus whether it hasn't occurred. Okay, so in that case you would suspect less bug infestations if they've been sprayed. Okay, but we don't know. We'll see in just a second how that plays out. Okay, so back to this. That's the first test. So the second test, and remember this is given that. Has anybody ever seen that symbol before? Okay, that's a new symbol. I figured y'all had not seen that. Now, how do we compute this? Well, there's another little formula we're going to take off to the side, and we're going to make sure we know how to do it, okay? The probability of A given B is equal to the probability of A and B occurring, so like their intersection, over the probability of just the given. Now, in a minute, you're going to see it's not really as hard as this formula makes it. The formula makes it seem way harder. I can also do the number, instead of probability, I can do the number that are in A and B divided by the number that are in B. So essentially what I'm doing is the number in the intersection out of the number in the given. In a minute, it's going to make so much more sense to you. So we'll kind of come back and talk about that in just a second. But that's the first test. So put a little asterisk here because you have to kind of go off to the side to compute that. Oh, I know what it's doing. It's my, when my paper touches the thing, it won't work. Okay. So the second test, let me show you what that one is. Now there are times, depending on how your information is given to you, that the first test won't work. But I always like it because it makes more sense to me. It just makes a lot more sense, but I don't know if it will to you guys, so we give you two. So the probability of A and B, does that equal the probability of A times the probability of B? Because guess what? If they are independent, this is the formula you're supposed to be using. Remember that from a few minutes ago? Okay. Now, so the question is, once you figure out your values and you see if they're equal or not, if they're equal, they are independent events. So students can figure out sometimes they're not equal or they are equal or whatever, but they don't know what that means. So this is what you're going to take away from this. For both of these, equality implies independence. So if they're equal, you have independence. That seems real simple right now. Later, it's not going to. Okay? Okay, so those are our two tests, so let's do some examples. So I actually have a handout for you, which you can take notes on. I would probably suggest doing this, even though they are on Blackboard and you could probably annotate over it, I just think it's kind of hard to do that. Got one more. Okay, so now we're going to go do the little example we just looked at. Okay, so go down to this example here with the aphids. Okay, so we're doing pretty good on time. Yeah. Oh, good. Did everybody get one? Because I thought I was actually about to run out. Okay, so what we're going to do is we're going to say, let A be the event having aphids. Okay, let's let event I being sprayed with insecticide. So we're going to test. And we're going to say, well, first of all, let's put our labels on here. A is for aphids. Then I'm just going to say not aphids. They either have them or they don't. Here, I'm going to do I, meaning they were sprayed, or using the complement, meaning they weren't sprayed. So I'm just assigning things. So here's my test. Does the probability of having aphids equal the probability of having aphids if or given the insecticide was applied? Do you see how this test makes perfect sense? No? No. Okay, so let me ask you a question. The probability overall to have aphids versus the probability to have aphids if they were sprayed with the insecticide. Which one do you think is supposed to be lower?
The second one. The one that was sprayed.
The one that was sprayed should be lower, right? If there really is something going on with the data and if the insecticide really works. If it doesn't, then who knows what's happening, okay? So let me go back and ask you, does it make sense how this test tells you whether you have independence or not? The probability for aphids is going to be exactly the same as the probability to have aphids given the insecticide was sprayed if they're totally independent of each other. But what you expect to happen is those that have been sprayed have a lower chance or lower probability of having aphids. So see how the test works, like mathematically? Let's do it, and then it'll start to come around to you. Okay, so the probability to have aphids, what is that going to be? 26 over 80, because I'm looking at those with aphids out of the total. So the question is, does that equal to the probability to have aphids if they were sprayed with the insecticide? So let's first start by looking at the table. Where are my sprayed by insecticides? They're right here, the top row here. So I have 52 total. My given count is 52. 52 were sprayed with the insecticide. But how many of those had aphids? 12. So it's going to be 12 over your 52. Okay, now, let me remind you of something. Well, first, let me give you a second to pause. Do you understand the probability for aphids?
Yes.
It's just those that have aphids, period, out of the total. Here you're looking at a given condition, that they were sprayed. So you're only focusing on those that were sprayed, the 52. And then you're looking, out of those 52, how many had aphids? Okay, so reminding you about the formula I introduced, the probability to have aphids and to have been sprayed with insecticide divided by the probability for the insecticide. Remember how I told you it's probability of A and B divided by the probability of B? So you're looking at the probability of the intersection, or the number in the intersection, divided by the number in the given. You guys remember doing this in an earlier math where you focus in on the givens? You did it in probably 7th grade, I think. I think it was 7th grade. Unless you didn't come through the accelerated and you jumped on later, then you probably would have been 8th grade? 9th grade? 8th grade? Okay. Y'all done it. Okay. If you haven't done it, it's okay. We'll figure that out. We'll learn it. All right. So this is the new, or the little formula that I gave you. Let me just show you right here. I just want to make sure you understand where it's coming from. When I introduced the test for independence, this is this formula I did all this work on over here. So we looked at the number in the intersection. The intersection was aphids and insecticide. That was our intersection. And then divided by the number of those just sprayed by insecticide. So I used that formula. Okay, just want to point that out because I know it gets tricky. All right, so are these independent? So first of all, what are we getting? 0.325. And does that equal 0.231? It does not. So exactly what we thought was supposed to happen did. If they were sprayed with the insecticide, the chance of having aphids goes down, which is what you want, right? Is it significant?
Yeah.
Not really. And actually in AP Stats we learned how to test if that really is significant or not, if that's a big enough difference to see if it's significant. So that's later down the road. So these events are not independent of each other. And I'm going to show you exactly what you should write, because the probability for aphids does not equal the probability of aphids given that the insecticide was applied. Okay, now, so that's the first test. We're going to go to the musical instrument example and the left and right-handedness. Are you also writing that? Mm-hmm. Okay. You actually have to do this on a test, yes.
So when do you use the probability of A and I over I?
When you want this right here. This is this piece right there. So the probability to be, y'all listen, so the probability to have aphids given they were sprayed by the insecticide is going to be the intersection of aphids and insecticide divided by the insecticide.
Oh, so that's not a different thing. You were just
It's not a different thing.
Okay.
It's not a different thing. Most of you can use the table and just do it kind of with common sense, not common sense, but you prefer to probably use the table than to use the formula. But we are supposed to teach you the formula, and I also want to show you the formula is matching what you usually do at the table. So when you learn this, I'm sure your teacher taught you focus on the given and only do the number out of the given. So given something has happened, you want to focus on those where it happened, and then those that have aphids out of those. So it kind of makes sense with the table, but it does also fit with the formula. Yes?
Why are they not independent? Like, I don't understand.
Okay, if they were equal, they would be independent. So they're not independent because if the insecticide has been sprayed, the probability for aphids isn't the same as the overall population. It goes down. So knowing that they have been sprayed with the insecticide we know that changes the probability to have aphids. It goes down. So it's similar to our replacing or not replacing. When we don't replace the marble, the next event's probability changes. It's a different scenario because we didn't put that marble back. So it's that kind of thing. So knowing that one thing has happened changes what happens next. Knowing that the insecticide has been sprayed, the probability for aphids goes down. That means they're not independent. Say, remember, equality, which we don't have here, implies independence. Equality implies independence. Equality just means you have independence. Okay, let's do the next little at the top of the page here. Now, I'm going to use the other the other test. So I'm going to use test 2 here, which is basically, let's get some labels here. Let's say right-handed and not right-handed. Let's say plays musical instrument and doesn't play musical instrument. So I'm going to use the test that says probability to be right and musical. Does that equal the probability to be right times the probability to be musical? That's the second test. Because if they are independent, that's the formula you're supposed to use. So we're going to use it to test here with this tail. Okay, so what's the probability to be right-handed and to play a musical instrument in our population here?
44 to 50.
44 over what?
50.
Or is it over 250? The
The
probability in our little population here to be both right-handed and to play a musical instrument.
44 to 50.
Not given that they play a musical instrument.
44 out of
What's the
250?
probability that a randomly selected person does both?
44 over 250.
44 over 250. Yeah, it's one of the bigger things students get tripped up on. So 44 over 250. So it is not a given, it's an intersection. It's where the two events coincide. So make sure you understand that. Now, what's the probability to be right-handed? 220 out of 250. And what's the probability to play a musical instrument?
50 out of 250.
So 50 out of 250. Okay? And now you can simplify all that down, but I think we come up with, this is going to be roughly 0.176, and this is also 0.176. So in this case, we're saying, knowing that someone is right-handed or left-handed does not change the likelihood that they play or don't play a musical instrument. These two events are independent. Equality implies independence, yes.
So, do you use the second test because it's telling you that they're independent?
No, I just used the second. Very good question. I just wanted to show you one of each.
So it doesn't matter which one?
I could have done the other one.
Okay.
And I would get the exact same results. So if I had done the first test, where probability of being right-handed, does that equal the probability to be right-handed given they play a musical instrument? Same outcome.
Okay.
Same outcome. Okay, so these events are what? Are independent. Okay, I'm going to leave it at that just for the sake of time, just making sure. It's because the equality implies independence. So equality Okay, now, so let's keep going. We are going to do number 3. Now this gets into some more, like, just another type of the same thing. So for number 3, a basket contains 6 bottles of apple juice and 8 bottles of grape juice. You choose a bottle without looking, put it aside, and then choose another bottle. What's the probability that you choose a bottle of apple juice followed by a bottle of grape juice? This you know how to do, right? And you don't really even need the formulas. You're using them, you just don't know you're using them. Okay, so go ahead and figure out what you get there. So I'm going to say the probability to get apple juice times the probability to get grape, given I just got apple juice. But again, I'm not really necessarily using that. I'm just looking at it and saying there's 6 out of 14 here, times, and it'd be what? 8 out of 13 here. So whatever that gives you, that would be your answer.
30 over.
Miss Morgan?
Yes.
If we get our answer in decimal, what do you want us to round to?
I would say 3. Get in the habit of rounding to 3 decimal places here. So did anybody put it in the calculator and get their answer? Because I have not.
30 over 182.
What's that?
30 over 182.
Okay, so 30 over 182. So what does that give you when you do it in the calculator?
30?
Oh, wait. 48 over,
Yeah.
yeah. So what does that give you?
0.26, yeah, 0.263. No,
Point-
0.264.
4 or what? I couldn't hear you.
It's 0.264.
0.264, okay. Very good. Now, if you had multiplied this across and left it in fraction form, do go ahead and simplify the fraction, okay? If you run out of time on the test, then simplifying the fraction might cost you like a half point. It's not going to be a big deal, so don't fret about that too much. Okay, now, number 4. You have a set of 10 cards that are numbered 1 through 10. You shuffle the cards and choose a card at random. You put the card aside and choose another card. What is the probability that you choose an even number followed by an odd number? Well, how many even number cards do we have? 5. So it'd be 5 out of 10 times what? 5 out of 9. Very good. So the probability to get an even is 5 out of 10. But the probability to get an odd, given that you just got an even, is 5 out of 9. So you've been doing this, you just didn't realize it. Okay, so like I said, we're just going to kind of jump around. Go to the next page.
Miss Gordon.
Uh-huh.
Can I go ahead and leave?
Yeah. Well, how much time do we have? Let's do number 1 quickly. We're going to do number 1 and 2. Hopefully that's kind of the goal.
Is this our homework?
No, this is not your homework. Hold on 1 second. Your homework is actually in the textbook. And it's on Blackboard, so you can see it there. Now the textbook, remember, I did put a picture of it, but you can go online and get the textbook too. Okay, so there's 2 ways to get it. So that contains 5 red, 3 green, 4 blue, 8 yellow. Find the probability of randomly selecting a green marble and then a yellow marble if the first marble is replaced. So this is where you do have independence, right? So it's just going to be the probability of getting a yellow is what? Oh no, wait a second. Getting a green first is 3 out of what? 20. And then times what? 8 out of 20, because remember you put it back. Okay? So, and I'm just setting these up for you real quickly. So this is the probability of A and B when there is independence. It's the probability of A times the probability of B. So it's just simple. That is when you have independent events. Yes?
Okay, I like understand how you do the couches, but I don't understand all that equation stuff.
Okay, for now, focus on just kind of doing what you would normally do, and we'll slowly work those. Like, try to make the formulas and equations make sense to you. It takes a few days for it all to kind of gel. It really does.
If we don't use the formulas on the test, do we get like points to go?
If I recall correctly, there may be a place here or there where we say, this is a scenario, which formula would you use? So sometimes we do that to make sure you're learning the formulas, but it wouldn't be like a big piece of the test.
Are we gonna like review all the formulas?
Oh, we review everything.
Okay.
It's already actually on Blackboard. The day before the test, I think I put up the formulas that we're going to be using.
Okay.
Okay, there is one that I think was a little bit harder. I think what it is, I have done an example And we're not gonna have time to go over it, but you may wanna look at this example on Blackboard, okay? So I did a test for independence for a pretty hard scenario, for a pretty hard situation. Let me see which one it is real quick. There's also gonna be a video on Blackboard, but y'all don't need to watch it because it's your class. So it's the same thing we did in class. So you can if you want to. We ran out of time this morning because of the fire drill in my second period. So the example that I did was number 3 on the worksheet you have, if you want to look at it.
What is homework?
The homework is in the textbook. It is, well, I'll have to pull it up, but if you just see it on Blackboard, okay? Easiest way. And I've attached the image, and also you get your online textbook. I know it's exhausting, isn't it?
Are the other units like a little bit
like
easier?
if this is gonna be all units, I might fill this box.
It's like, there's like 10 topics and you have to choose.